Welcome back to the second set of notes for Chapter 11, Advanced Placement Chemistry. We're in IMFs, Intermolecular Forces, and Solids and Liquids. We left off somewhere around here with polarizability. The more electrons you have, the more polarizable you're going to be, and the greater your atomic mass, the stronger your dispersion forces will be. So now we can look at an example problem. What types of intermolecular forces exist between following molecules? So start here and say, well, everything has London dispersion forces, or LDFs. And so right away we can say dispersion forces, dispersion forces, dispersion forces, and then pretty much I would start probably drawing these. If you just have one hydrogen bonded to one bromine, then you are going to have bromine, a very electronegative atom, hydrogen, a not a very electronegative atom. They have a huge difference in electronegativity, and so it's going to be dipole, dipole, or polar. If you draw methane, which we've drawn a lot, carbon surrounded by 4 hydrogens, each of these lines terminates at a hydrogen, then you get a molecule that is pretty symmetrical. It's surrounded by atoms of the same electronegativity, and so we're going to get an even distribution of electrons, and it's going to be nonpolar. And so then really the only IMF we're going to have, if this is nonpolar and the next methane is a nonpolar, is going to be London dispersion forces. And then sulfur dioxide, we could draw that as well and go a double bond to oxygen and a double bond to oxygen and say, boy, that's another one where it's pretty evenly distributed, and so we're probably going to see LDFs only in that molecule. And so let's take a look at it. HBr is polar, dipole-dipole forces. There's also dispersion. Nonpolars, dispersion, and then they show you in 3-dimensional space how it's evenly surrounded. And then sulfur dioxide, oh, shoot, draw that wrong for you. Sorry, they went with 1, 2, 3, 4, 5, 6, 7, 8, and they only formed 3 bonds on sulfur instead of 2 double bonds, which makes sense because sulfur only has 2 valence electrons. I guess it doesn't make that much sense. Never mind. I thought it would be clearer with the periodic table, but it's really not. So sulfur dioxide, they did a double and a single bond. And when they do a double and a single bond, that leaves these electrons up here. So if we have 2 unbound electrons, it's going to distort our shape, and we're not going to have an even distribution of electrons, so it's going to be nonpolar. So now we'd have to change our answer, seeing that I drew the wrong Lewis. This is the Lewis they want us to go with. It would have to be London dispersion forces and dipole-dipole forces because it's polar now. So sorry about that. There you have dipole-dipole forces and dispersion forces as well. So hydrogen bonding is a special dipole-dipole bond between hydrogens and nitrogen, oxygen, or fluorine. I remember FON, like a baby deer is a FON, F-O-N. Those are all the molecules, or atoms rather, that can form a hydrogen bond. And so you just look at something and see if it's got a hydrogen bonded to one of these, it's probably going to be hydrogen bonding. And they show you here hydrogen can be bonded to either A to another molecule B or from A to another molecule A. As long as A and B are nitrogen, oxygen, or fluorine, any of these would work as hydrogen bonding. And so here you see some hydrogen bonding occurring in water, where we have the hydrogen from water interacting with the lone pair from the other oxygens. That's hydrogen bonding. Hydrogen bonding between nitrogen and hydrogen, and then nitrogen, oxygen, hydrogen, and fluorine. All of these are examples of hydrogen bonding. And it's kind of odd because, of course, hydrogen only has 1 electron, so it's not really going to be able to do both of these at the same time. It can't form 2 bonds, but it's going to kind of alternate quickly between them and be shared. And so here you have nitrogen, oxygen, fluorine, where they are on the periodic table. Shows you that they're very, very electronegative, and it shows how hydrogen is interacting here on the end of the oxygen. And this would be a carboxylic acid, C double bond OH, and its hydrogen here is interacting with the negative end of this oxygen, and then this oxygen here is interacting with the hydrogen from water, and so we're hydrogen bonding on both of these. So why is it considered special? Here you can see how our boiling point changes as we move across a period from carbon and nitrogen, fluorine and oxygen, to sulfur and chlorine, to selenium, to tellurium. What happens to our boiling point? You can see that the ones that have hydrogen to oxygen, fluorine, and nitrogen are so much higher than these others, hydrogens, to anything else. And so what we get is a type of bonding with hydrogen that is a lot stronger than what we would expect. And so this is a trend we should see, and this is the trend that we do see. And so we put those separate because they're especially strong. All right, so properties of liquids. Now we're going to the liquid solids part of this chapter. We're done with the intermolecular forces. So surface tension, if you've ever seen maybe pepper floating on water, or a little water glider bug on the surface of a lake, you've seen surface tension. It's the amount of energy required to stretch or increase the surface of a liquid by any unit area. If you have really strong intermolecular forces, then you're going to have a really high surface tension. And so we get a few properties of liquids we need to know. The first is cohesion. It's the intermolecular attraction between like molecules, or you could say interacting or bonding between like and like. And so water bonding to water is cohesion. And so here's cohesion, where this doesn't look like water since it's depressed so far. It might be something like mercury, but one mercury atom bonded to the next mercury atom, that's cohesion. And then adhesion is an attraction between unlike molecules. And so adhesion would be the mercury interacting with the glass tube. And so here you can see in water example, we have adhesion, which is the water bonding to glass, unlike itself. And then cohesion is water bonding to water, molecules that are like itself. And so those two forces working together can allow water to climb a thin tube. So if adhesion is very strong and cohesion is not that strong, we can climb a tube. If cohesion is super, super strong and adhesion is very weak, then we can actually be depressed down the tube because you're really trying to cohere with the other mercury atoms. So viscosity is a measure of a fluid's resistance to flow. It's sort of like how thick or gummy a liquid is. If you ever heard the expression slower than molasses in January, that's a viscosity reference. Here's a few different liquids and their viscosities. And they show you how thick, I guess, basically a liquid is. Strong intermolecular forces are going to give you a really high viscosity, because the stronger intermolecular force you have, then the more strongly you're bonded to your neighbors, and so you're going to pour a lot slower. So let's look at water. Here's the 3D structure of water. Water is super weird in comparison to other liquids because generally the trend for density is less dense as a gas, more dense as a liquid, and most dense as a solid. And so that pretty much carries for like everything we know. The solid state sinks in the liquid state, and the gas state floats above the rest, that sort of thing. Water is really odd because when it freezes, the solid state of water is actually less dense than the liquid state, and so ice floats. And that's kind of a cool thing because in northern latitude aquatic ecosystems, if this didn't happen, then pretty much the whole ecosystem would go extinct every winter because the ice would freeze, sink, freeze, sink, freeze, sink until the entire lake was a big block of ice. But since that ice floats, it's actually going to form a layer of ice on top of the lake and insulate all the water below it from the very cold air temperatures, and it really allows everything to survive, and it allows guys to go out and ice fish, I guess, so why not? Here's the density of water and how it changes as you start to increase its temperature. The density goes down quite a bit, but when it freezes, the density does come down a little bit, and that allows it to float. So it's kind of a cool structure right there that allows water to do that. And it's this hexagonal crystal lattice that traps a lot of space and a lot of air and is not as dense as the liquid that allows that to happen. So A crystalline solid. If it's a crystal solid, then it possesses rigid and long-range order. In a crystalline solid, atoms, molecules, or ions occupy specific positions. And so crystals basically means it's a solid that's very orderly. Now, not all solids are really orderly. There's solids like an amorphous solid. Amorphous is like without form. It does not possess well-defined arrangements or long-range molecular order. This would be something like glass or frozen honey. It doesn't form distinct crystals. It forms crystals without shape, which is why when you break glass, it creates all these weird little jagged edges. So we break down crystalline solids into a simple cell called a unit cell, and that's the most basic repeating structural unit of the solid. And so here's the unit cell. So some sort of solid structure that has a pattern like, I don't know, solid sugar or salt or anything. This could be one salt, ionic formula unit, and then the salt crystal that you see in the salt shaker would be repeating units of this same unit cell that's like one sodium and one chlorine, and then it all makes this together. And so they call lattice points the atoms, molecules, or ions that are bonding to the next unit cell. And now here's some shapes. I don't think that you would need to commit these names to memory to be successful in just kind of your general everyday life. But simple cubic is a cube. Monoclinic, it's like a tall rectangle. Tetragonal, another tall rectangle. Orthorhombic, rhombohedral is kind of this tilted over diamond thing. Triclinic is a taller tilted over diamond, and then hexagonal is the water example that we gave earlier. So there's a few types of cubic unit cells. The first is simple cubic, which means we just kind of stack them up in a cube, and in space filling it would look something like this. Body-centered cubic would be, we have this stacked up cube, but then there's one right in the middle, and so all the ones around the cube kind of attach to that one in the middle. That's body-centered. And then face-centered cubic would be, we not only have one on each corner of the cube, but we also have one on each face. Like if this were a die in three-dimensional space, then you'd have, a number on this face of the dice, a number on this face of the dice, a number on this face of the dice, a number on this face of the dice. Each of those numbers in this example is one kind of unit cell arrangement. And so that's what it looks like in space filling. It kind of looks like a whole bunch of nonsense, but it's not. There's order to it, I guess, if you know what you're looking for. And so when we arrange identical spheres in simple cubes and we cut the middle out, it looks something like this, with this middle point being X here. And in body-centered, you see we cut the middle cube out and we see there's one sphere in the middle, and then we just get little corners of others. So we have a corner atom, an edge-centered atom, and a face-centered atom. This isn't something that you're going to have to draw, but one is shared by 8 unit cells, the other is shared by 4, the other is shared by 2. And so it just depends on where the atom is in the crystal, how many unit cells it's going to be shared with. And then our simple cubic, one atom is in one unit cell, and so we would have 1. And then a body-centered cubic, there's 2 atoms in a cell. And then in face-centered cubic, we've got 4 atoms in a cell. So between edge length and atomic radius, there is a relationship. Here's your formula for that. Not something I plan on having you calculate, but it can be done. So here's one called closet packing, hexagonal and cubic. Basically, you make your three-dimensional shape, your triangle, and then you stack these in the gap of each of these. It's sort of like bowling pins, but stacked on top of one another, and then one on top here, and then that gives us our hexagonal structure in the end. And if we put 3 on top, that gives us a cubic structure in the end. So an exploded view kind of shows you how this hexagonal structure is arranged. These 3 are in the gaps provided by these molecules close together, and then we add another 7 on top of that to get a hexagonal structure. And then here is your cubic structure. So here's an example of a problem. The unit cell edge length is 409 picometers. Calculate the density. So if density is mass over volume and volume is area cubed, then we can say we have 409 picometers cubed. That gives us a volume in centimeters cubed. And so there's 4 atoms per unit cell. So our mass of 4 silver atoms is going to be 107.9 times 4. And then we can get our atoms in a mole. And we end up with 7.17 times 10 to the negative 22nd grams. So we can find density because we have our mass and we have our volume. And it'd be 10.5 grams per cubic centimeters. So that's how you could solve something like that. And unfortunately, with that, that's all the time that we have for this video. So next time we'll pick up with X-ray tubes for our third set of notes. Thanks.